and you plot the charge state against the number of residues, you can see there's clearly a trend here. And that trend is basically one additional proton for every 6 residues. Here is a very, very highly charged peptide. So this is a histone tail peptide. And it has, I've marked them here in red, it has 16 basic residues. But it cannot acquire 16 charges. It can only acquire up to 9. And the charge density does not exceed this figure of MZ 600. Here's an even stranger case. This is pepsin. Pepsin is a highly acidic protein. It only has 3 basic residues. When you spray it under native conditions in electrospray, what you see is you have charge state 8, 9, 10, 11. So additional protons are being acquired, and they are not corresponding to the expected protonation state in solution. But it gets even worse. This is pepsin under denaturing conditions. Under denaturing conditions, you can acquire up to 47 protons on that ion. And that's not unique to pepsin. If you look at the maximum charge state for any proteins you want to look at, I just randomly chose 38 proteins and I plotted them. So this is the maximum protonation state. This is the difference between the number of charged residues and the maximum protonation state. And you would expect that everything would be either sitting on this line or would be below it. But actually, everything is above the line. What this says is nearly all proteins have too many protons in electrospray. And it's not just proteins. This is DNA. This is an oligonucleotide. This is sprayed in negative ion mode. This is in positive ion mode. So most people who work on oligonucleotides will tell you you need to work in negative ion mode. And it works, that's fine. But if you change the polarity, what you discover it works actually much, much better. There is 40 times more signal here than there is there. It's the same analyte, it's the same buffer, just change the polarity. And also, you now have an additional charge state. Okay? So you have 5 protons sitting on that oligonucleotide. So I hope I have made it clear up to this point that for species above the Rayleigh limit, I'm trying to explain what that means, but basically large species, the protonation state is absolutely independent of the charge state in solution. Protonation state is determined by surface area. And just to make that point, this is a beautiful experiment done by Stefan Reichenbach, who is now Professor of Chemistry here in Oxford. And what he did is he's done this, ion beam deposition mass spec. That's his speciality. And you can isolate different charge states of cytochrome C, which is done here, and then he can deposit these onto a special grid, and he can do scanning tunneling microscopy of those ions. And this is what he sees, that for the high charge states, we have a linearized structure. As we go down the charge state, they become progressively folded until we have a compacted structure here at the lowest charge state. These are all denaturing spectra, but you can see here that the surface area of your protein is, the charge is determined by the degree of folding in your protein. So the maximum charge state, this, as you would expect, corresponds to the largest possible surface area. For a protein, this is the linearized structure. You cannot exceed that surface area. And that's why there's a maximum charge that you can't exceed. For globular proteins, you can approximate the radius. From Grandori lab, they generated this relationship, and we've tested this, and this works. This is a protein from the SGC. This is KCTD17. It forms, quite unusually, it forms a complex, a 60-mer complex, which is effectively a Buckminster fullerene. It forms a perfect hollow sphere. I don't know if it has any biological relevance, but it forms this structure, and we have a crystal structure for it. When we put this in the native mass spec, we can measure the average charge state here, plus 79. We can put it into that formula, and we calculate that the radius is 85.5 angstroms. If you then measure the radius from the crystal structure, it's almost exactly the same.
Sorry,
yes.
You've been talking about maximum charge state. Now we're
No,
talking about
I'm
average.
talking here, this is the maximum charge state for a denatured protein is its linear structure. This is a native fold.
So in this case we should use average.
I'm using average charge
Not
state, yes.
maximum.
So actually, strictly speaking, it's not the average charge state. The average charge state for this distribution would be roughly here. This is actually the modal charge state. So it's the most abundant charge state. And that's the one I would use for this calculation. If you calculate the charge radius for the range of proteins and you plot this against the hydrodynamic radius, it's a reasonably good fit. It's not a perfect fit because the calculation assumes that you have a perfect sphere. And of course, for most proteins, you will not have a perfect sphere. But you will, the globular proteins, generally they will approximate a sphere, and they will, if they do, they will fit in the cell. So, where do the protons come from? I said that the protonation state is not dependent on the pH of your buffer. Where do those protons come from? Well, they come from here. Basically, this is diagrammatic representation of electron spray source, and what you have, because of the application of your voltage here of about 3,000 volts, you are generating protons at the source by electrolysis. And those protons are going to be in excess, irrespective of the mobile phase pH. Here's an example of protons that are in charge that is in excess. This is electrostatic charging. Okay? In the case of electrostatic charging, you have an excess of charge. The charges are mobile, and they obey Coulomb's law. Okay? So Coulomb's law basically means that they will partition themselves equally amongst the available surface area to achieve minimum free energy. And exactly the same thing is happening in electrospray. For species above the Rayleigh limit, an excess of protons is always available. And those protons are mobile over the molecular surface, and they obey Coulomb's law to achieve minimum free energy. So what evidence is there that protons are mobile? Well, there is evidence for this. This is infrared photodissociation spectrum to cytochrome C. And so this is in the gas phase, and what you can see here is there is a signal here. This particular peak does not occur in the liquid phase. It only occurs in the gas phase, and it increases with charge state. So the authors who published this, they could not explain this, but this is the signal of the mobile proton shell. Also, if you study fragmentation, peptide fragmentation, mobile proton theory has been around for years, and you cannot explain peptide fragmentation without it. And basically, this experiment we've done in the SGC. This is a singly charged peptide of BSA, and when you fragment that, you are going to generate a charged fragment and a neutral fragment. Neutral fragment you cannot detect. But what this spectrum tells you is fragmentation and charged fragments are being generated from both termini. That is only possible if protons are mobile. So, going back to my original question on the KCTD, sorry, for the original native spectrum I showed you, why do you have multiple charge states in the first place? Why should you have multiple charge states for a single native species? Well, the reason you do is because proteins are flexible in solution. I want to illustrate this with two extremes, okay? Here is an extremely thermally stable protein. Streptavidin is the most thermally stable protein known. This is its native spectrum. It was acquired several decades ago, and effectively there is almost one peak, just two for this one, but if we measure the width of that ion distribution, it's basically 1.5 charge units wide. Now compare this with tris tetraproline. This is spectrum generated in SGC. It's an intrinsically disordered protein. Effectively, it has no thermal melting curve. And you can see here the charge distribution. If this is a native spectrum, the charge distribution is almost completely flat. Okay? If you measure the width of that, it's 8 charge units. I now want to show you something. This is not protein. Okay? It has components of protein. So this is diphenylalanine monomer. It is a dipeptide. Okay, so it has the chemical constituents of a protein, but it is not protein. If you take this monomer and you heat it up and then cool it down slowly, it will generate these fibrils. Okay, it generates these rigid fibrils. When you spray these into mass spec, what you get is you get spectra where you can measure the charge state for each residue. So each point here is a different species. So we started with 2 units, 4, 6, 8, and so on. And all of these have one charge state, +1, but only +1. All of these also have one charge state, +2, +3, +4, +5. So the charge is increasing as we increase the molecular size, but the number of charge states is 1 for all of them. You will never see a protein that looks like that. Every protein anybody has ever measured has multiple charge states. This is non-protein. If you compare that with the number of charges for proteins, these are native proteins. So here we're measuring the protein residue number here against the distribution of charge states. And for native proteins, we have a relatively narrow distribution of charge states. However, if they're denatured, this is a synthetic peptide, these are a range of denatured proteins, you can see that the number of charge states is actually very, very wide. So if you're comparing these, what we're doing is we're saying this is increasing surface area, and this is increasing molecular flexibility. So how do we explain spectra? How do we explain electrospray spectra? So the thing to understand is protein structure is not 3-dimensional. It's 4-dimensional. Okay? Protein has a structure. That structure has molecular motion. So we're interested in surface area. The surface area will not be constant. It will change with that molecular motion. So it's continuously changing. Well, what will it look like? If you were able to measure the surface area, you would expect the surface area distribution. You would expect that the protein will spend most of its time in this surface area, some of its time with a slightly larger surface area, some of its time with a slightly smaller surface area. So you'd have this, you'd expect Gaussian distribution. If you take that Gaussian distribution and bin it into integers, into whole numbers, it's going to look like this. Okay? If you now compare that with the native spectrum, that's what we're looking at. Those integers are protons. We can explain denatured spectra is slightly more complicated. Denatured protein surface is continually changing due to extensive random molecular motion. So denatured protein does not have structure. It has all kinds of conformations. But it cannot exceed the maximum surface area. The maximum surface area is linear. It cannot exceed that, which means that you don't get a Gaussian distribution. You get a skewed Gaussian distribution because you cannot exceed this maximum surface area called the linear structure. But in mass spectrometry, we don't measure charge, we measure the inverse of charge. We measure 1 over charge, mass over charge. So you need to plot the inverse surface area so that your distribution is now going to look like this. And then we do the same thing. We bin those into integers, and those integers are protons, and your spectrum looks like this. So we can use this. This is very, very useful. We can use charge radius to measure changes in thermal stability. I want to show an example of this. So this is trypsin. So trypsin, it's active at pH 8. So we can spray in ammonium bicarbonate at pH 8. And this is the charge distribution that we get. If you measure the full width half maximum, it's 4 charge units. You can stabilize trypsin by storing it in hydrochloric acid. You are not denaturing it. This is the normal way to store trypsin. Put it in hydrochloric acid, it becomes inactive. When you put it back into a high pH buffer, it retains its activity. If you spray it in hydrochloric acid, which you can, you now have a native distribution, but it's shifted, so you've got a more compact structure, but the width of this distribution is now narrower. This one was 4, this is now 2.5. There is a third thing you can do with trypsin. Okay? Thermo will sell you smart digest trypsin. It has been thermostabilized. So what they've done is they have methylated it, and it's then stable at 70 degrees. If you, oh yes, sorry, I just mentioned, here, so your protonation state decreases from pH 8 to pH 1. Not what you're expecting at all. So if we now plot thermostabilized trypsin, you can see that it almost exactly mirrors the pH stabilized trypsin, although the distribution is not quite so tight. It's 3 charge units. There's another thing we can do. We can measure conformational change. So this is oral kinase. It can phosphorylate itself. So if you incubate aurora kinase with ATP, over time it will generate different phosphorylation states. So this is unmodified. That's phosphorylation state 1, 2, 3, 4, and 5. What I've done here is plotted the charge radius calculation for phosphorylation state 1. If we now do that and overlay it for phosphorylation state 2, you can see there's almost no change. Phosphorylation state 3, very similar. However, phosphorylation state 4, you can see that the distribution has shifted to the right. Phosphorylation state 5, sorry, phosphorylation state 4, phosphorylation state 5. So what are you actually looking at here? What you are looking at is a 1% increase in the surface area. But also, when I did this experiment, I thought, well, I should expect to see a gradual change. But of course, you're not going to see that, because phosphorylation is a switch. You are switching the protein from one conformation to another. And a switch is not gradual. A switch is on or it's off. So here, this is phosphorylation off, and this is phosphorylation on. This is an example of using native mass spec for looking at protein-protein interaction. So this protein HAO1 is a, well, if you ask Wyatt, if Wyatt's group, Wyatt will take this tetramer. Everybody in Wyatt's group says tetramer because it's a crystal structure for a tetramer. Native mass spec is saying, yes, that's absolutely correct, but it's also an octamer at the same time. And the octamer has a mass of 350,000. What we've done here is this has now been incubated with this compound. This compound was made by a medicinal chemist specifically to disrupt this interaction. And what you can see now is the spectrum has changed. We still have the tetramer, we still have the octamer, but we now have a new species. And it's this, sorry, that's the tetramer, that's the octamer. This is the new species, and this is the predominant species, and this is the septamer. And the mass corresponds to 7 units with this compound. Also, though, you'll notice we have a 4th species which we didn't have before, and this is the free monomer with our compound also bound. Okay, so that's all I want to say. Just to recap, native mass spec allows you to measure accurate mass, molecular interactions, structure, post-translation modifications, size, stability, and conformational folding, and they are all determined in a single experiment. In native mass spec, all native characteristics are preserved. Sample preparation and ionization conditions are critical. The instrument parameters have to be optimized for high MZ transmission. Any electrospray instrument can be used. Electrospray ionization is independent of charge state in solution. Independent of charge states in solution. It occurs in the liquid phase, and it's a direct measurement of surface area. So we can use native mass spec for quantitation of denatured, partially unfolded, folded states. This is an essential QC requirement for recombinant proteins. It's a direct measurement of protein stability. It's a direct measurement of ligand binding, protein-protein interactions in solution without the need for immobilization or the need for conjugation. And conformational changes, such as phosphorylation, ligand binding, equivalent to 0.5% difference in surface area can be measured. That's all I want to say. Next week.
What does that last bit mean?
Sorry.
5% in surface area?
You missed the talk, I'm sorry. Well, okay, we can go back. Go back quite a long way. Okay. Yes. So this is measurement of surface area. We can measure this. This is accurate to within 2%. Changes in conformation. Here. So this is the difference between these 3 distributions and these 3 distributions. Okay. Yes, next week it will be small molecule accurate mass analysis, not on Thursday, but on Friday. Okay, thank you. Any questions? Yes.
Why no UNSO? And what's the threshold
Yes.
before you start to do
I wanted to show you the picture, but there just wasn't time. So we've done some experiments with DMSO on HAL1.
Yeah.
The problem with DMSO is it's non-volatile. So people say, well, it's okay, we have a small, when you're doing screening, it's normal to use DMSO, and I think it's true to say it probably doesn't have any effect because it's very low concentration. The problem is it's non-volatile. So in electrospray, as your solvent droplet desolvates, you are concentrating up the DMSO.
So you're shooting your protein at 100% DMSO.
Yeah, pretty much,
Yeah.
yes. So what we've seen is DMSO changes the structure. I have data on HAL1, you have a look at it. The structure is actually totally different in the presence of DMSO. So what I would recommend is if you're going to use it for screening, I would evaporate off your DMSO and resuspend it in something that is mass spec compatible like methanol.
Okay, thank you.
Any questions? Okay, thank you.
Go back to Aurora spray.
Yes, absolutely. This one.
So this is
Yeah.
envelope, right?
This is, okay. So how do I get this? Okay.
Yeah.
So what we're doing here is we're using this expression of the relationship between charge and surface area to calculate the radius, and then for each charge value, so basically this is intensity of the
Yes.
of
So-
the
yes,
NZ
so basically
species.
you
This is
think-
intensity
yes.
NZ species. Effectively, what we're doing here is this is charge.
Mhm.
Okay, so this is effectively the inverse plot of the MZ spectrum.
And you recalculate it into angstroms.
Yes,
Okay.
yes. So this is the theoretical radius of a spherical protein which has the same charge.
Mhm.
Yeah.
Okay. So it's an inverse to what we do.
Yes. Yeah. Yeah. It's one of the problems in interpreting native spectra is, usually you plot your x-axis increases from left to right. With charge, because you're plotting MZ, it decreases from left to right, so it's a little bit confusing. But this is plotted this way.
So do elongated proteins behave very differently? You have, rather than a globular.
Yes,
spherical.
you cannot do this calculation on a denatured protein. It's only valid on a native protein, and its validity is based on how globular it is. So if it's a perfect sphere, I showed earlier, if it's a perfect sphere, it's a perfect relationship. But obviously, if your globular protein is slightly elongated, it's not going to fit that
Did you
relationship.
ever try some kind of anchoring the repeats which will be very, very, very elongated? How do they?
I'd like to try that experiment.
So,
Yeah,
we
I've done
should
it.
have such proteins.
Yeah, no, we should do that. Yeah, definitely.
And what limitation is there other than DMSO in terms of looking at particular proteins with highly charged terminal? Does that matter?
I'm not sure I understand your
Also,
question.
like if you have histone proteins.
So I showed a histone.
Oh, okay.
earlier.
No,
Do you want to see it again? Hang on.
So it doesn't matter about the nature of the protein, as long as it's native, it has some type of native conformation,
So
particular charge.
this is, I didn't really fully explain this. So this is histone protein. What this slide was originally intended for is to actually show, you generally assume that if you have a peptide, it has no structure. This is what people generally assume. But this is the same peptide. This is sprayed under denaturing conditions. This is sprayed under native conditions. And you can see that these charge distributions are totally different. And the only way you can explain that is this has, this has a maximum of 9 protons, this has a maximum of 5. The only way you can explain this is that this peptide is folding backwards. But my earlier point to this is you can't use the number of basic residues in this extremely basic peptide to calculate the charge state, because it has 16 basic residues, but the maximum charge state here is 9. And you cannot generate a spectrum from a peptide which has an MZ value less than 600.
Sorry, I was
Okay.
late. I made it clear.
Okay.
Thanks.
All right. Thank you very much.